Halogens. Halogens, fluorine, chlorine, bromine, and iodine are reactive nonmetals. Although all halogens are highly reactive and toxic, the magnitude of reactivity and toxicity generally decreased from fluorine to iodine. The chemistry of fluorine differs from that of the rest of halogens in the following ways. Fluorine is the most reactive of all the halogens. The difference in reactivity between fluorine and chlorine is greater than that between chlorine and bromine. The weak bond in fluorine can be explained in terms of the lone pair of the fluorine atom. The small size of the fluorine atoms allows a close approach of the three lone pairs on each of the fluorine atoms, resulting in a greater repulsion than that found in chlorine, which consists of larger atoms. Hydrogen fluoride has a high boiling point as a result of strong intermolecular hydrogen bonding, whereas all other hydrogen halides have a much lower boiling point. Hydrofluoric acid is a weak acid, whereas all other hydrohalic acids, for example, hydrochloric, hydrobromic acids, are strong acids. Fluorine reacts with a solid, with cold sodium hydroxide solution to produce oxygen fluoride, difluoride. You can see it. The same reaction with chlorine or bromine, on the other hand, produce halide and hypohalide. This reaction. Where X is chlorine or bromine. Iodine doesn't react under the same conditions. Silver fluoride is soluble. All other silver halides are insoluble. The element statine also belongs to the group of halogen family, 7 group. However, all isotopes of statine are radioactive. It's longest-lived isotope of astatine, which has a half-life of approximately 80 hours. Therefore, it's both difficult and expensive to study astatine in the laboratory. Halogens form a very large number of compounds. In the elemental state, they form diatomic molecules. In nature, however, because of their high reactivity, halogens are always found combined with other elements. Chlorine, bromine, and iodine occurs as halides in seawater, and fluorine occurs in the minerals fluoride, the calcium fluoride, or in chlorite, the sodium hexafluoroaluminate. In this table, you can see some properties of halogens. And let's study preparation and general properties of the halogens. Because fluorine and chlorine are strong oxidation agents, they must be prepared by electrolysis rather than by chemical oxidation of the fluorine and chlorine ions. Electrolysis doesn't work for aqueous solutions of fluorides. However, because fluorine is a stronger oxidation agent than oxygen. So you can see if fluorine were formed by the electrolysis of an aqueous fluoride solution, it would immediately oxidize water to oxygen. For this reason, fluorine is prepared by electrolysis liquid hydrogen fluoride containing potassium fluoride to increase its conductivity at about 70 degrees. You can see anode, cathode, and overall reactions here. And steam, the liquid hydrogen fluoride, and steel cathode, and you can separate fluorine gas and hydrogen gas. Chlorine gas is prepared in industry by the electrolysis of molten sodium chloride or by the chloralkali process, the electrolysis of concentration aqueous sodium chloride solution. It's called brine. Two of the common cells used in the chloralkali process are the Mercury cell and the diaphragm cell. In both cells, the overall reaction is this one. As you can see, the reaction yields two useful byproducts, sodium hydroxide and hydrogen gas. The cells are designed to separate the molecular chlorine from the sodium hydroxide solution and the molecular hydrogen to prevent side reactions. This one is side reactions, the reaction between chlorine and sodium hydroxide and hydrogen with chlorine gas. These reactions consume the desired products and can be dangerous because a mixture of hydrogen and chlorine is explosive. In this figure, you can see the mercury cell used in the chloralkali process. The cathode is a liquid mercury pool at the bottom of the cell, and the anode is made of either graphite or titanium coated with platinum. Brine is continuously passed through the cell as shown in the picture. And electrolysis reaction you can see here. The sodium and hydrogen denotes the formation of sodium amalgam. The chlorine gas generated this way is very pure. The sodium amalgam doesn't react with the brine solution, but decomposes as follow this reaction. And the byproducts are sodium hydroxide and hydrogen gas, also very important products. Although the mercury is cycled back into the cell for reuse, some of it's always discharged with waste solutions into the environment, resulting in mercury pollution. This is a major drawback of the mercury cell. In the laboratory, chlorine, bromine, and iodine can be prepared by heating the alkali halides, for example, sodium chloride, potassium bromide, potassium iodide, and concentrated sulfuric acid in the presence of manganese oxide by using this reaction. And in the laboratory, you can obtain small amounts of halogens. So, for example, you can obtain chlorine.